Okay. See, now we are going to talk about something very important. Of course, all parts are important, but important from the application point of view. What happened? What I termed these as, well, you can say dynamic effects. Let me call this as dynamic effects. See, when the ship is going in a rough sea, that is what is sea caving about, no? The ship is traveling here. You are interested in certain behavioral aspect of the ship. You want to find out how comfortable it is, etc. You are not really looking at motions per se by itself. What, for example, what you are looking at, things like whether the water here comes up, what we call deck wetness. Why? Obviously, you would see some ships, the bow has fully come down, water has rushed over it, and number of things. If there is equipment there, that may get washed out, there is a lot of load that comes on that, etc., etc. You are more interested in that. Okay, you are more interested in things like opposite. This bow may come up of water, even if it did not come up, it again hits back the water. As it hits back, suddenly you get a lot vibration load coming on that. That is what is again more important, because you are having an impact here coming. You have an equipment here, somewhere here. The load that comes on the equipment is proportional to the acceleration, say vertical acceleration. So, you would like to know what is the acceleration on that, because see, suppose I have a gun mount here in a naval ship, some mount which will typically be there, so it undergoes a lot of acceleration. What is the load coming on that? You would be losing speed if you go on a rough, compared to a smooth sea. For the same engine rating, if you are making 20 knots, you would probably make 18 knots or 17 knots in a rough sea. Or conversely, this is obviously a consequence of the fact that you have an increased resistance, and interestingly, this increase of resistance is a sea keeping phenomena rather than a resistance phenomena that you learned in the resistance course, because here the increase of resistance is a consequence of the fact that the ship is undergoing large motion, therefore it is spending energy. More propeller emergence. Backside coming out of water. So, there will be free racing and you obviously lose efficiency for that. And there are many other factors, motion sickness. People tend to throw up. All these obviously, and there are many more, I have just wrote few. All these are what are the dynamic effects, effect of the fact that the ship is undergoing motions. So, the ship is being treated, remember, as a rigid body. I have this as a rigid body. This full body is not taken in our study, and this is also largely true, because if you take it flexibility, it is going to be only a much smaller amount in terms of displacements. For example, if you take a elastic deformation, maybe about 1 feet maximum, whereas the heave motion may be few meters. So from the point of view of so it is important from structural load point of view. Besides, of course, I did not mention also structural load. The ship has to be designed to withstand this wave loads. But the point here is that we have studied ship motions as a rigid body, whereas a practical person would like to know this sort of stuff much more, because they are the one that is actually affecting your design. Now it can be found out that all of this are a function of that fundamental 6 modes of motions. All of these are function of that, which means all of this can be derived, okay, from fundamental those motions that we computed. So I have computed now so far those 6 modes of motion, actually 3 mainly, whatever the ship rigid body ship motion, let us say modes of, I can add here rigid body motion. What I want to know is these things, but now we will find out that all these are all what will get dynamic effects, and therefore since I can find it all up from my basic 6 modes, we call them derived responses at times. We call them derived responses because we can derive them from those 6 modes of motion. So from computation point of view, from determination point of view, RAO for 6 modes of motion will take you 95% of your effort that I kept telling every time. Spectrum will take 3% of effort or 2% or maybe 1% of effort, but if you did not do the spectrum, people do not want to take it. It is something like you cooked a curry and did not put a salt, something like that, you did not do a finishing touch. So people are not interested to look at that, but the effort is less. So let us not confuse practical importance with effort. Now similarly, derived responses, if you found out the RAO for 6 modes, we will find out, we will slowly go through that these derived responses can be determined just with 2% effort, because they are nothing but combination of this. Okay. So we will just take for example a deck wetness or slamming or something, or say vertical. Let us first take acceleration at some point. Let us take this ship here and I want to find out this some location vertical acceleration, just as an example to see how I can combine the two. Okay. This wave coming here. Now what is the acceleration of the vertical displacement of this point, this particular, say if I call this point P, what is my jet P of t? You will find out that this is nothing but the heave response of the ship. Okay. There is this and x into pitch, because if I call this to be x, the x of the point P, and this of course is theta. So this is x P theta, this is z. So I end up getting plus z minus x P theta to be the displacement of the point. Now why minus? That is another thing that we must understand. See what is happening. Remember, phase is very important here. I will come to that. Remember, in my coordinate system, actually speaking, what we are doing is, you can say here it is z plus x theta. with a proper coordinate system. Now you see here my z plus was this side, but which side was my theta plus? Now depending on which side you call theta plus. Now in our case here, if this is my y axis, this is my plus theta. So if that was my plus theta, that is this is my plus theta. See x y z, x y z I took. Now please understand this part, okay, depending on which side you call theta to be plus. See in this particular 6 degree of freedom coordinate system, if I were to call x to be here, y to be here, z to be here, then my theta is this side positive, bow down is positive. So plus x give me minus x theta of z. So therefore my zp in this case will become z of the hull minus xp into theta. On the other hand, if you are to calling this to be x and this to be y and you call this to be theta, then of course my zp is going to be z plus xp into theta. It is extremely important for us when we do a calculation to recognize which coordinate system you are using, because when you put in a computer or a table form, you are only adding numbers. After all, a negative number is nothing but minus 1 time positive number or the same number in the opposite direction as far as displacement goes. You see here, normally what happened, 2D plot, this is why I wanted to spend little time here, 2D plot x, y and you call it, sorry, this is not here, this is this thing, x to y when you go is theta, but when you do a 3D I am using x, y and z. If I use it, and if you do not want to use it, if you use x, y and z, it will be opposite. But if you use, in fact if you use 3D, you can also use the other way, like in submarine we do, we call this y, this as y and this as z, but even there minus z plus xp theta will come, it will be the same thing. Okay. So if you use 3D, z and xp theta are of opposite side. What calls z plus for positive x, remember this x is positive, if you go on the other side it will be different. So anyhow we have this. So what is happening now is interesting. See now I will work on maybe, so I have zp equal to z of the hull, this is all function of time remember, minus xp into theta. Now this z of the hull is z heave, well z heave, let us put some numbers here, z, okay, let me call it z heave, okay, amplitude of z heave, or rather let me call it za. Za is the amplitude of this thing into cos plus or minus, let us see what they call, okay, minus into when into, sorry I keep forgetting here, into theta a, okay. Basically theta is theta a cos omega t a plus epsilon theta etc., or in fact I prefer to do it in a complex domain, you know. I always keep meeting, let me write it here then. Oh. No, I am going to write it again because this full thing can be written as we can write this here P. See, what I wanted to say here, like it's a question of manipulation only. I mean, a pure algebra, I just wrote it here. You can always write it in terms of algebra. See, if I add two cos curves, okay, what will happen? This line, look at this line. This line will come out. If I were to add the cos, I will just show here and then I will show. So, if I add two cos curves, see, let me just write it again here, because sometimes people don't see it. This full thing will turn out to be a term here into cos something. It can be written in this form. You can always break it and write in this form. See, when you have this cos A, see cos A, cos B plus sin A minus sin A. See, it will be cos omega t E t cos epsilon z minus sin omega t sin epsilon z. Here again the same thing. You combine them together, you ultimately end up getting some term into cos omega t plus some. Okay. This term is what we call the absolute amplitude, that is ZPA, and you will end up getting cos of omega E t plus you will end up getting EP. Now, the same thing I am writing here, in fact, sorry, here this is I omega t, it will become, this is going to be, what is happening is that here sometime you want to operate them in terms of complex number. The complex number sometime operation is easier. After all, cos this is nothing but real part of E I omega t plus epsilon z. This is a real part of this. So, you add them all up, you will end up getting something, and you introduce something called a complex amplitude. Basically, this is going to become ZPA into EI beta, that is this part. This term is this term and this term combined, because this is a complex number. So, you can write that way. This is not very important. Why I am writing this way is that sometimes it is easier to do manipulation of addition when you write this way. We have done that before. If you recall, we have done similar kind of thing before in wave mechanics, when we were doing resistance, wave resistance, etc., combining the various waves. Manipulation of sinusoidal signals are sometimes easier if you work them in complex domain. That is my point, but never mind the complex part. You can always write it down. Let us say if you do not like it, I can add the signs. Now, I end up getting this, where of course what will happen, ZPA will be of course function of, you will find out this will be expression. It will be something like function of ZA, of course XP theta A epsilon Z epsilon theta, something like Z, this I am not sure, it will be something looking like that, plus or it may be minus here, I do not know, Z A XP theta A cos maybe, something like that, it will look like that, something of this nature. And similarly tan of, it will look something like ZA etc., etc. I am not writing the full thing because you can verify that. It is a simple trigonometry, there is nothing to it. Okay. This if you write, you can write in this way. It also makes sense if you look at this from other point of view. This is a sine signal, this is another sine signal of the same frequency. If you add it all up, you will of course be getting another sine signal of the same frequency, right. This is a sinusoidal signal, this is a sinusoidal signal of same frequency. If you add them up, you will get another sine signal of the same frequency. What will matter is the amplitude and the phase, that is all. So, this is what the amplitude and the phase, you end up getting it. So, I have got this, let us say that. Now, the important point is for me is this way. So, I have this part, I have here. So, I know now my ZPA, not ZPA, sorry, ZPT equal to ZPA cos omega E t plus this I know. I want to know acceleration, very simple. I just have to do is minus, is it? No, sorry, yeah, minus. So, I know this, I also know this amplitude. So, I now know this. Now, you see, typically what would happen, I will know this signal fully, therefore, that is point 1. Point 2 is that I am mostly interested in the amplitude part of it, because mostly when you design, obviously the maximum value that will come is this value with the minus, without the minus sign, absolute, the maximum value acceleration, that means if I were to call it ZPA dot dot is going to be omega E square. Okay. So, this is going to be my maximum acceleration. So, therefore, I can easily find out what is the load coming on that gun mount. This is very simple. Now, let us look at same example of deck wetness. When is the deck wetness occurring? Now, we have to actually have this wave part also coming. Now, you see here, now of course, I need to draw a wave, a reference point here. Now, I have this ship. There is a point here. So, this point has moved up with respect to my reference point to an extent of ZP. Okay, or whatever the reference point you call. Now, there is a wave here. What is my eta? Eta is of course given by A cos k x minus omega t. Remember, I am calling this to be the 0 phase. So, I am putting the phase 0. So, I have got this and I have got ZP t, this is also t here. This is omega e we have to write. We have to transform that to omega e, remember this is k e. We have to write that in terms of omega e. First of all, you can we have to change it to encounter period, that formula we all know, omega e t plus. So, what is the relative difference between the two for a given point? Now, actually here there is a the question you have to remember that we are doing it from with respect to this ZPT, means how much a given point is going up. So, I will come to that point. Let me say that this is becoming a, I will just draw it again, a reference point. This point, this is my mean line, obviously vertical displacement of that, this particular point, which is otherwise at the free surface on bow. This particular point P star, this point has having a relative displacement with respect to the water given by Z P star t minus eta t. Okay. Now, so this again I can figure this out by simply working it out in the exactly the same fashion, because I have my ZPT is given as ZPA cos omega E t plus eta p. So, if I will just put here minus eta t, this makes it minus A cos. Now, you see k e x will be for p, that is, well, we are calling it p star, which is going to be of course depending on what you take, typically lambda by 2. sorry, it is typically the 4 peak point except 4 peak point. I will just come to that, omega E t, or minus, we call it minus 9. Now this xp here, remember, is this, it is about, remember I am writing this about L by 2, but not exactly, because remember this point is at Cg. In fact, it is actually, I can call it this plus LCF, I can call it that way, because you know Cg for a balanced chip is going to be above LCF, no, not LCB, LCB. It is okay, it's, I mean, it's, you know this value for a particular chip. So once again here the interesting point will come. See here, this to when I add, again another cos 1 cos curve. So this is going to be again here some kind of a z, let me call it this bar, let me call it r, I will call y, I will say y r, I am calling it, into cos it will again look like that. When you see, just similar way another sine curve is added with another sine curve. Remember here x does not, this part is a constant, because this is L by 2 or whatever, this is a constant. This is a constant for a given xp star. So this value is constant. Given xp star you will get this. We are using of course one single wave, so you end up getting this value. So what I will end up getting is here that I will end up getting this. With this gives me like this. Now this is what we can call, this is what we can call relative vertical displacement of bow. This is the amplitude of that. This is the time, this is my, let me call this side now ZRT. This is ZRT equal to this, okay. That is my relative vertical displacement. Example, heave is this, pitch is this, when I combine the two I end up getting a displacement looking, oh well it, I should not draw it, you know, like with the face, same face, so something like that. This is say let us say you end up getting that. Now on that I have got my, I have to use the red line, wave. At this location my wave may have been like this. What is therefore the relative displacement? The difference between the two. So this is what I am plotting here. This is my what does it mean? This means at any given, this is a wave here, my ship is here with this axis, this point I am taking, I want to find out what is this distance. Okay. If I was standing here, I will find out how much it is. Now we can work out the deck wetness from freeboard, because what is happening, if this distance is negative, see this is here minus coming, right. If it is plus and more than this distance, then I would say at that time, in other words, if I will say that Zp relative exceed, say this value I will call it some, say h, water on deck, So, you can see this diagram, for example, this, suppose this was my threshold deck limit, then this instant and this instant water has come on deck. Very simple, you know. So, I can find out this water coming on deck and its relative spec. Now this is okay. This is relative vertical displacement. Now let us look at the bottom slamming. The same thing, bottom emergence. If I find out there is negative value, that is this value is actually this bottom is coming out. That is just the opposite of that, right? I know this height. So, if I will find out, then what is the chance of its, see opposite side here, if this is coming something like that, bottom here, so I will know that the bottom is coming out. So, I will be able to find out both the parts. So, what I mean therefore is that, see, the interesting point is therefore what we are doing, we are combining heave and pitch, that is all we are doing, and because they are sinusoidal we can always get a sine curve. And once I can get a sine curve, now comes the, let's look at this acceleration part once again. So, I have got this. What about my irregular C? Can I use that for spectrum? What I have done is of course regular waves. You see here what we have done in relative acceleration, what we have done here. Let me look at this acceleration part, because we can just go from one to other. See this. I have got the acceleration, this full history I have got, okay, by adding a heave and pitch. The second question you want to ask is, how do I get a spectrum for that, you know? Well, the question is that I will use this in RAO, this by omega E, that is it. My relatives the spectrum, okay, let me give this as an example, that is easier. So, I end up getting, we are picking up the case of acceleration here at some point. So, I have got this Z P, this is the point P here again, star star T, which I have found out that is obtained as eta never mind the minus sign. So, what is RAO? So, you find out the same way. So, S simple. Now, you may want to ask the question, where is the phase information coming? Is there a phase between heave and pitch, like you know, we are already having a number, but understand that when I got this value, this has the proper phase between heave and pitch combined. For example, if heave and pitch were of such a phase that they will give large ZPA, then I will have a much large ZPA. And once again this sort of example. See, if the heave displacement was like that and the pitch displacement here, let me write it here, pitch displacement here, because you know easier, x, let me plot x theta directly. If x theta was in phase like that, what do I get? I get a graph which is like this. Okay. What I mean is that, see, when heave, blue line is, that is vertical displacement due to pitching only at that location, at that location. If they happen to be in same phase, obviously this has a phase information between the two, then I get this red line. On the other hand, well, I put the other way around, anyhow, if the blue line was happens to be opposite, then what do I get? I get my red line to be smaller, maybe here. So therefore, what I find out? I find out that my ZPA is a of course we have seen that function of ZA theta A x P. Importantly, very important for us to understand this, Z, see this is important, location is important. Why I am mentioning that, there is a reason for my mentioning, because you see some of the students, some people are always confused in one thing. When I do this spectrum, we say that there is no phase information, right? We keep saying, see, this term phase is very important. When we do this spectrum, I am saying that I am adding waves 1, 2, 3, 4, 5 with random phase, there is no phase information in between. So quite often people, students have a confusion. Here he is saying there is no phase. On the other hand, if that was the case, to find out, like I stretch it like incorrectly one step, if there is no importance of phase when it comes to response in irregular waves, then when I want to find out relative, the heave and pitch combined motion, why should I have a phase of heave and phase of pitch important? You see, I am in one hand I say for it, so when I want to find out the acceleration spectrum of a combined heave and pitch motion, why should I have phase information embedded in it? Because I am saying that after all waves having no phase. The difference is like that. See, the most important part is like that. What here I said is that I am adding this by getting this by adding regular waves at different phase, but for each regular wave I have a heave and pitch, and this must have that phase information for the given regular wave between heave and pitch. So when I want to do this phase information, we have to understand that this phase information is indirectly there for a given wave. See, phase information is there for a single sine wave. What I do not have is the sine waves are being added separately, but for a given sine wave I must have a phase, because if I did not have a phase, as I said here, if I did not have a phase, my this two line would have given me different kind of response. So if that was the case, if I had a heave of say 1 meter amplitude, pitch of say 2 degree amplitude, then I would have had, regardless of the phase information, I would be always getting at a given x the same amplitude, but that is not true. For example, we see this long wave. Why this phase information is again important? You see that the phase information is there. This long wave, my ship is going like this. Interesting. Here I will leave it to you to work out for the long wave part. Find out that my relative displacement of this relative displacement, that is ZR, this remains constant. Is an assignment problem for you. Find out in long waves when z follows wave, theta follows not zp, sorry. I will tell you, when you do that, you will end up getting into one problem of k. What will happen, I tell you, you are going to find out this, and you will find out here there is no response, but what will happen is that you are going to do this. See, when you use zp t minus eta, and in eta you will write eta equal to a cos k e x minus omega e t, and when you use this term, you will end up, you will probably think that there is a problem, but because what happens, strictly speaking, when this was 0, only then this is 0, but when it is not 0, you know, I am just giving a hint. See, strictly speaking, this point is following that. When I take another point here, my x is not 0. Actually what I am meaning is that zpt minus eta at x equal to 0 will become, strictly speaking, equal to 0. But when I use at x equal to x p, some number will come, but what is happening is, why I want to tell you is that, see, remember what we said, long wave, what is k e? K is actually 2 pi by lambda, and this is x. So if this is very high with respect to this value is going to be very small. So this is going to be very small, close to 0. This is the approximation that you will have to find out. See, after all, we have started saying in this particular calculation that my long wave, which means my ke tend to 0, at that limit my z tends to a amplitude of wave, and theta tends to d eta by dx. And if I were to plot this all up, I will end up finding that my z r, which is zp minus eta, will tend to, that is very simple, because you can see from this picture, if the ship is following this, obviously at this point, if you are standing here, you are going to find out the water wave 5 meter below, all the time 5 meter below, which means with respect to you, wave does not vertically displace. In fact, this is one of the thing why, now you will understand why short waves or inertia dominated motions are more important in some sense than long waves, because in long waves you find out I do not have the risk of my green water shipping, risk of my bottom coming out is very less, whereas it is the other extreme end where my motions are inertia dominated. When added mass and damping are not ignorable, at that time my phase is opposite, my relative motion is different, ship comes down, water comes up, etc. And the interesting point, the more interesting point, you see that I will tell you this, when omega tends to infinity, ship, we will just discuss this part physically. Agreed? But when omega tends to, well, I would not say small, smaller, ship has a phase with wave. When I say phase, of course, he says there also is a phase, but that phase is 0. There is a non-zero phase, what I mean, like understand that. When I say phase, means they are basically more closer to out of phase. Of course, it is never out of phase fully. This will be 0, this will probably be 90 degree, 70 degree, like that. So there is a chance more, but there is one more point there. You see, the other point is like this. This I will discuss in the next class later on, but usually bottom slamming. You take bottom slamming part. This part has come out, then it hits back. What do you think this impact load will depend on? It will depend on the, well, strictly speaking, velocity, how fast it comes in. If you do an impact study, if the thing comes out very fast, that is its velocity v, that becomes important from impact load. Acceleration is the load itself, but remember, acceleration is the load itself. It is that if you are going to go very fast, impact it, see on a free surface, if you are going to impact this body at a certain velocity v, you would expect the force to be more. So what I am saying, the slamming load will obviously depend on, which we will discuss next class, the threshold value and all that, on v. Well, what is v? V vertical of this point is actually z of the point relative velocity, if I take into dot, and this is going to be omega e times z r. That means omega is important. So here comes the situation, when omega is higher, I have a chance of this slamming more, and because omega is higher, my slamming load also is more. You get the point. See, when I am going on a tsunami, a very long wave, I do not bother whatsoever for ship motions, because it is such a long wave, you do not even feel it. That is why we do not speak of ship motions or sea keeping in such long waves. I mean, I am giving a practical derived response or what, nothing you do. A tsunami type of wave may be having 20 minutes period. If you are going to take a roll 20 minutes time, you cannot feel it. You drink your cup of tea, you do not even know there is a wave that passed by or whatever. If it is an extremely small wave, then also the energy is so less that a large ship does not feel. It is actually always this everyday wave, somewhat on the lower side of higher side of frequency, lower side of period, where I have all kinds of problems, and that is where I have to do sea keeping. Why I am saying this repeatedly is because this is important, that we are always talking of sea keeping between a given range of frequency of waves. We do not talk about very short waves, ripples. You go to any ocean, you will find small ripples, you do not care. You talk of large waves, very long, you do not care for a ship. There are certain large waves you have to care for, like offshore structure. You care primarily for these waves, and you have seen, and we have seen in your ship strength calculation, you always have chosen what? Trochoidal wave is not the point. Well, that's one point. What my main point was length. What was the length you chose? Why? Why do you chase length of the wave? Is there no other waves beyond the length of the wave? Ship. So who says that? First of all, who said that there is maximum bending moment? Where did you get the information? So you think, obviously it has come from experience. Most calculations have shown that if the wavelength is similar to the ship length, then there is large bending moment that comes in, load comes larger, which means the effects are much larger. Of course, you draw a nice picture. In fact, the present theory tells us it is not exactly lambda equal to L, it is about 1.05 to 1.1 L where the maximum comes. But nobody knows, it will be around that. See, what I am now given information is that modern research shows that when lambda is approximately little over L, about 5 to 10% over L, that is where largest bending moment occurs, not when exactly equal to L, but that is a variable number. So when you do a conservative design, you obviously don't know what is the number, so you took L. But main point is that it is around L, or it lambda by L around 1, or if it is 1, if I call this to be 1, then of course waves around this maybe around 0.5 times to say 3. This range lambda by L, is where you would expect most effect coming. Tsunami waves here or whatever very long, do not bother. Small ripples here, you do not bother. Okay. So, this is the part. Now, here again I am trying to say this, as you go this side further, my slamming and all are less important. As I go this side little more, around this area, my slamming and all are more important. Okay. Fortunately or unfortunately, if it was this side slamming more important, I had also omega lower, so my load would have been less. See, not slamming important, what I meant, if you go this side, my chance of bottom coming out or deck getting wet is less itself. So, the question of my load does not come. This side this happens more. So, there is a chance of its coming out more. On top of that, having come out, it has to re-enter, it will do much faster. So, here my goes like that, and every time bottom comes out and impacts. So, it comes out and impacts over a short time. So, if this time was more, then you would have had bottom coming out and impacting lower time, and the impact load would have been less. But unfortunately, this is happening on this one I do not have so much chance. So, I just want to tell you these aspects. So, we will discuss next class onwards important part of the other thing, that slamming, deck wetness, what do you want from the spectrum. Normally you do not want how many times like what is the chance of slamming, etc. What you will want, deck wetness, that in 100 or 1000 cycles or in a 24-hour day, how much time you may think the deck will be wet. So, the thing that you want is something else, that we will discuss. How do you get those quantities from spectrum? That is, it will say that in 1000 cycle, how many cycles you expect the bottom to come out and slam, not the slam load itself. How much percentage of time you think the deck will become wet. These things also can be obtained from the spectrum, which we will discuss how we can statistically derive those. But today's lecture was main point, which I am going to end with saying that, see, all this and more we will discuss, seasickness, etc., etc., all are functions, pure functions of those 6 modes of motion. Our AO for all those derived response, or if I were to write, this is the last one for today. So, it is this that where the calculation lies, this where the application lies. Okay. So, with that I will end today's class.